Hi, my name is Riha and my colleague Pavla Sretrova. We are presenting the Buqouy problem. It's the problem developed by Czech aristocrat Buqouy, who was the first one who investigated mechanical system with a varying mass. In 1812, he explicitly formulated the correct dynamical equation of motion for the case when a moving object mass is changing. The object is the following consideration of an ideally flexible fiber lying reeled on a horizontal plane. Determine its motion when a constant vertical force is exerted on the end of the fiber. This motion is described theoretically and simulated using Wolfram Mathematica has been shown. Moreover, this motion is successfully realized experimentally. Experiment data are compared with theoretical results. Thanks.
Okay, good afternoon, everybody. I'd like to start by thanking you all for coming to our talk today. My name is Pavla Sretrova and my colleague's name is Riha. We work at Palacký University in Olomouc in the Czech Republic. We are going to talk about mechanical system with varying mass, specifically about the Buqouy problem. At our university, we solve this topic as a student project. To start with, I will briefly explain basic principles of the Buqouy problem. After that, my colleague will continue with explanation of an experimental arrangement and comparison of experimental data with simulation. So let's start with a historical background. The problem we will talk here is associated with the name of Count Graf George von Buqouy. He was Czech aristocrat, really well educated and gifted inventor. Buqouy was born in 1781. He was the first who investigated mechanical system with non-constant mass. In 1812, he explicitly formulated the correct dynamical equation of motion for the case when the mass of the moving object is changing. In 1815, he presented his result at Paris Academy of Science to the leading scientists of the time, such as Laplace, Poisson, or Fourier. His ideas did not attract attention and soon became forgotten. So the first explicit example of a system with a varying mass suggested by Buqouy in 1814 is the following. Consider an ideally flexible fiber lying reeled on a horizontal plane. Determine its motion when a constant vertical force is exerted on the end of the fiber. So, denoting the position of the end of the fiber above the horizontal plane by x greater than 0, we make the following natural simplifying assumptions. The vertical gravitational field is homogeneous, the fiber is thin, and its linear density eta is constant. The fiber reels off without friction at the origin of the x-axis during the upward motion. The fiber smoothly disappears at the origin of the x-axis during the motion downward. That is, the part that has already landed on the plane does not move. The problem could be modeled experimentally as a vertical motion of a balloon with a heavy rope hanging down. So the motion of the fiber is determined by Newton's law, where P is the momentum of the moving part of the fiber, F greater than 0 is vertically upward oriented constant force, and the mass multiplied by the gravitational constant is the oppositely exerting weight of the reeling fiber. Supposing the mass is given by eta multiplied by x, where eta is constant linear density of the fiber. Therefore, the equation of motion has the following form, equation 2, and after a modifying form of 3. A stationary solution represent the equilibrium situation such that the end of the fiber is situated at a constant height. It's equation 4. So it seems that the problem may be reduced to finding the solution of equation 3. However, this equation only describes the upward motion of the fiber. It is only correct form a growing x. It means that the first time derivation of x is greater than 0. The reason is that only in such a case the resultant force is responsible for the rate of change of the total momentum of the fiber. The first term in equation 5 corresponds to a velocity change of the already reeled off part of the fiber which has the mass. The second term expresses the part of the momentum which in the time has to be delivered by the resultant force in order to give velocity to a piece of fiber of mass lying at rest on the plane. In this way, the piece joins the moving part of the fiber. In the case of downward-oriented motion, the situation is different. The appropriate rate of change of the momentum only corresponds to the velocity change of the already reeled off fiber. The second term in equation 5 represents the rate of change of the momentum of a piece of fiber which, with mass, which in time lands on the plane. Its velocity has to suddenly decrease from the first time derivation of x to 0. However, the forces considered above are not responsible for this change. Such a change is due to the interaction between the fiber and the plane. Therefore, the second term in equation 5 must be ignored when the first time derivation of x is less than 0. Thus, we can write the equation of motion in the following form 6. To look for a solution for the first time derivation of x greater than 0, we can integrate the equation 2 to obtain the following equation 7, where c is integration constant depend on initial conditions as following in equation 8. Equation 7 can be rewritten as this following equation 9. When this term VEF EF is effective potential for the case of upward motion, this may be formally interpreted as a conservation law of the total mechanical energy, corresponding to the motion of fictitious particle with unit mass in the force field with effective potential. So there we have a simulation. I will run it. Yes. So substituting 9 to equation 3, we obtain the following equation 10, where on the right side here, of the equation is effective force. Then we can make the following conclusion. For c greater than or equal to 0, we observe that effective force is less than 0 and initial velocity must necessarily be greater than 0. The initial condition of velocity equals 0 is only possible. Then the effective force is greater than or equal to 0. For any value of the exerted force, there exists a maximum height x big M. The solution x small m has the meaning of the starting point of the upward motion with 0 initial velocity. To look for solution for the first time derivation of x less than 0, we can integrate the equation 6 to obtain the following equation 11. It follows these conclusions. For every potential level higher than effective potential, there exist two turning points for which it is valid following. The coordinates of these points fulfill the conditions 12, as you can see on the graph here. Necessarily x2 greater than 0, therefore the upper end of the fiber can never fall down back on the plane. So let's move on. So during the upward and downward motion, we can simulate the complete motion. If the downward motion follows the upward motion, the turning point x1 is identical to the maximal value x big M. Similarly, the turning point x2 becomes a new minimal value x small m for a subsequent upward motion. To describe the complete motion of the fiber, we thus have to alternately join solution of equation 9, valid for the first time derivation of x greater than 0, with solution of 11 for the first time derivation of x less than 0. So in our model, the equation of motion 3 and 6 are rewritten in united form. The motion of the fiber exhibits damped quasi-periodic oscillations. Small oscillations are close to harmonic ones. It can be shown that the time interval between two subsequent passages in the case of upward motion decreases in time, while the analogous time interval for the downward motion increases in time. So we have there simulations. On the x-axis is the time, which can we change maybe like that. And in this square we have initial conditions. We can change it, as you can see. So now it's my colleague's turn.
Thank you. This is a simulation. Of course, we were curious how this simulation fits to the experiment. First of all, we had to arrange some experiment like this, and if you see internet, for example YouTube, there are many experiments. There are many school experiments you can see, but not experiment like this. So this was also motivation to create some experiment, to arrange some experiment like this. I will show you recordings of this experiment. What we need as mass point helium filled ball, and also some appropriate fiber, because you cannot arrange the experiment with some light fiber, because we don't have a drone, for example, for recording. It's some high altitude. So we found some appropriate metallic chain with good linear density. I will show you this experiment. Our colleague will come who teach school experiments at our department. This is Čeněk. And you can see these oscillations. For measurement of the movement of this mass point, we are using with our students the freeware called Tracker for video. It's freeware for video analysis, and this is a screenshot from this program. It provides us some Excel table or something of data of dependency of the height of the ball on time. If we upload at first the data, we can show how these oscillations, based on the equation in the theory, how my colleague presented, you will see the final result. No, I'm sorry. This is only downloaded data and the dependency on height of the ball on time in the experiment. But in next slide, we will compare this experimental data with the solution of this differential equation. The best fit we get is this one. As you can see, this is not very good because the oscillations, especially the damping of oscillations, is very small, smaller than the experiment. And that's why we think about it that this air resistance on the ball movement should be taken into account. So if we do this and look on this experiment like small motion, small velocity motion of the ball, we used Stokes' approach to air resistance of the movement. It means linear dependency of the force of the air resistance force on velocity. This is this term, and after several arrangements, you have to rewrite the last differential equation to this form. So this term is additional for this. So if we use this equation and again compare the best fit with the experiment, we obtain this result. It's much more better than the last one. There are some differences also, but I think there are many errors during the experiments. For example, if you remember the recording, the movement, it is very difficult to log the movement of the ball into line. So it could be probably the problem. Maybe some more errors during the measurement, but I think this result is pretty good for us for this movement. Thanks for attention. If you have any questions.
This was pretty big. What was the details? We will have expecting some additional effects. You've taken the buoyancy also into account? You've taken the buoyancy because you said it's helium, right? helium and air? You have taken this also into account somehow?
Excuse me, the
Buoyancy. Because it's helium and air, right? There's a buoyancy force. You say this is canceling out.
The power. The force that because the difference in density of helium.
I don't think there is in the room is a difference in density in the air in 2 meters. I don't think so.
Right. Okay, the other thing,
Because
you tried some
we
other chains? You tried some other change to get better results or something?
we suppose constant force to the ball.
Okay.
Yeah, we didn't suppose it could change with with attitude.
We just did this experiment, but you couldn't, for instance, you didn't say put it in a big box and say put just nitrogen in there, and then instead of replacing the air by nitrogen, you would get it in the box. You can take this.
It could be a problem. I think if you use light fiber, and the movement will be much more high. I think we should compare it.
You try to use the find fit command in mathematics?
No. The problem is that this is the simulation is numerical differential solve, numerical solve of differential equation. So we try it, but it was better to do it manually, since we see the constants from the experiment. But if you do it, I think you should use nonlinear model fit, and you have two parameters to set in this. Okay, thank you.